Okay, here we have another initial value problem where we're going to solve this differential equation shown here and given these two initial conditions, but we're going to use the Laplace transform technique. So here we take the Laplace transform of each of these terms, y double prime plus 4 Laplace transform of y prime plus 6 Laplace transform of y is equal to the Laplace transform of 1 plus the Laplace transform of e to the minus t. The Laplace transform of y double prime is s squared y of s minus s y0 minus y prime of 0 plus 4s y of s minus 4y0 plus 6y of s. Laplace transform of 1 is 1 over s. Laplace transform of e to the minus t is 1 over s plus 1. We note that the initial conditions here are 0 for both y of 0 and the derivative of y is equal to 0, evaluated at t equals 0. So this is 0, this is 0, this is 0, so we can just factor out y of s. So we have s squared, we have plus 4s, and we have plus 6. That's equal to 1 over s plus 1 over s plus 1. Dividing out s squared plus 4s plus 6, we have 1 over s squared plus 4s plus 6 plus s plus 1 s squared plus 4s plus 6. That's in our denominator, and we have a 1 in the numerator. Now what we do in this case is we form a partial fraction expansion after we put these in common denominator. Now putting this in a common denominator such that we have s plus 1 s squared plus 4s plus 6. So this yields s plus 1 here and then plus s here. So that's just 2s plus 1 all over s plus 1 s squared plus 4s plus 6. Now we'll do a partial fraction expansion in this last expression here, and we look at the roots as s equals 0, s equals minus 1, and this is a complex roots. Since we know complex roots, its inverse Laplace transform will be a combination of sines and cosines. So that's why I have here cs plus d over s squared plus 4s plus 6, because we know the s is associated with a cosine, and then the d term here is associated with the sine. And we'll show you that when we complete the square, because we did this earlier. Now, putting this in a common denominator, so we have a s plus 1 times s squared plus 4s plus 6 plus b times s squared plus 4s plus 6 plus cs plus d, and then s times s plus 1 is just s squared plus s. And this is all over s plus 1 times s squared plus 4s plus 6. That's equal to y of s, which is equal to 2s plus 1 all over s plus 1 s squared plus 4s plus 6. Okay, since the denominators are exactly the same, we can just look at the numerators. So that would be just 2s plus 1 is equal to a s plus 1 s squared plus 4s plus 6 plus b s s squared plus 4s plus 6 plus c s plus d quantity multiplied by s squared plus s. Now, to save time in this partial fraction expansion, it can be shown that a is equal to 1/6, b is equal to 1/3, c equals to -1/2, and d equals to -5/3. Now, calculating the coefficients that we just did and substituting into y of s, we have 1/6 over s plus 1/3 over s plus 1 minus 1/2 s minus 5/3 in the denominator all over s squared plus 4s plus 6. But we did this earlier. An example, we can do an expression where we separate it into the s term, so we can complete the square of the denominator before, and so that's like s plus 2 over s plus 2 squared plus square root of 2 squared multiplied by -1/2. And this minus 5/3, we saw that term here is square root 2/3, square root of 2 over 3, and that's square root of 2 over s plus 2 squared plus 2. And this is 1/6 1s plus 1/3 1/3 over s plus 1. Now we can apply our inverse Laplace transform of this, which is just y of t is equal to 1/6 plus 1/3 e to the minus t minus 1/2 e to the minus 2t sine of cosine of square root of 2t minus square root of 2 over 3 sine of square root of 2t. So here's our result shown here.